Hi, everyone. This is ME 5390 Advanced Thermal Design. Today, I'm going to continue chapter 2. The homework problem, maybe some other time. I like to move on, okay? And I maybe post the homework solution so that you can look at it. I think one of the basic heat transfer to the fin earlier, we discussed with H, P, K, A over C, theta B, hyperbolic tangent, MB. Okay. Where I think this is equation 220. You can look at and we defined MB. What is a M? What is M is H, P, K, A, C, and B is B. Okay. So what is a H? Please answer. Can you answer? Please. Time clicking. Oh no. Somebody.
What's the question?
What is H?
The convection coefficient?
Yes, yes.
Transfer coefficient.
Yes, please answer quickly, okay, so that I don't have to wait. Because I like to remind you, I'm sorry. So what is P?
Perimeter?
Yes, you know, it depends on the shape. In a rectangular, I think the perimeter is, what is the perimeter? L times T. I think if it is correct, say yes. Somebody. I trust. Yeah. Okay. What is a K?
Thermal conductivity?
Yes. Yes. What is the AC? A of C.
That's the area of the cross section?
Yes. Cross-sectional area. Yes. So what would be this cross-sectional area? Help me.
Would that be L times, well, that's the A sub P is L times T.
L times T. I think so. cross-sectional.
That's the A sub P. Is that the profile area is the same as the cross-sectional area?
What is a profile area? Anyone?
That's B times T.
So I think you should know that. Anyhow, the zeta B is not inside the root. Don't confuse. What is a zeta B? Anyone in terms of symbol?
Temperature of the base minus temperature of the ambient. Ambient.
Yes, thank you. That's the zeta B. So what is the name of B?
That's the base. Or
No. Name
profile length.
profile length. Okay. Yeah, sometimes yes, we use base, but this B I'm talking about, this B is a profile length, the most important profile. I'm sorry, the students, if you say base, that's a way behind. Study hard. Okay, this B is quite different base. M is, we defined M here. Okay, so most important optimal is profile length. The question is profile length and T optimization. This is a optimum. Keep in mind. L is not. L is not the. Yeah. So this is basic, and then we developed. All we developed. Okay, this is basic. There is some assumption. Hyperbolic tangent MB. What assumption? Anyone remember? Come on.
Is it the constant volume or?
No. Somebody else.
Are you talking about the adiabatic tip?
Yes, thank you. Adiabatic tip. We neglect the heat transfer at the tip. So adiabatic tips, small, but we neglect it. Okay. So that the much simpler forms and more powerful optimal analysis, we did it actually. So let's look at it. This is really nice. I developed no any other books because I just developed and then put in the book. Dimensionless, normalized, optimal, I would say. Okay, so all the curves are optimal. All curves optimal, but depend on the u value. So u value is 2hl over k power to the half. Once you, because h is not really optimum, h should be known. L is not optimum, L should be known. K is a property, then you can calculate the u. So once u, this is u, this is u. Once you have curve, okay? This is the curve for Q. Okay, this does not guarantee optimum, but the relationship of Q, capital Q is a actual Q over that. Okay. So there are several cases So U is given, and volume is given. Look at that, volume. Volume is given. Then do you think you can find the optimum? Answer is yes. So how do it? Suppose, I don't know, depend on the U, depend on the U. So suppose U is 0.05, suppose, okay? Then volume is given. Do you think you can find optimum? Yes. How to do it? I'm looking at this curve. Okay, this curve. I'm looking at this curve. This is the U curve, 0.05. So volume is given, but what is the optimum? This heat goal of heat sink goal is a maximum heat transfer through the heat sink. So that if Q is maximum, the actual Q must be maximum. So that the maximum, I'm looking at this. Okay, so that approximately I can find V, small v. Once I have a small v, I know the volume, then I can get the T. Look at that, I can get the T. So once I have T, well, the volume is what? Volume is what? A P L, whatever the volume. APL, yes or no? Say yes.
Yes.
Yeah, this is AP, so this is L, it must be yes. And then AP is BT, BTL. So volume is known, T is known. Do you think you can calculate the B? Yes. So B and T optimal, you find it with the constant volume. Okay? So it works. Now, I have another question. You can raise a question anytime. Now, maybe volume is not known, but the heat transfer is known. Do you think you can determine the optimum? Yes or no? The same U.
Yes.
Answer is yes. So U is 0.05. So same, this must be the curve we're interested, but where is the optimum is, since K is known, but we don't know AP, L is known, theta is known. So how can I find it? I think we look at the maximum here. So this is the Q. Once Q is known, then do you think you can, AP is BT? Still, I don't know which one is which, BT, but here, the V is known. So here is BT. Do you think you can find the B or T? Yes or no?
Yes.
Yes. Here is one equation. Here is one equation. You can, anyhow, I think you can do it. Here is a APL is a V. I think what you can do. What you can do is this APL is a V. So if Q is known, small q is known, you can calculate the V. And then once you know the V, I think you can once a V is what is the V? Is APL. AP is BTL. So V is a BTL, something like that. So anyhow, so V is known, and yeah, something you can. What happened? This is weird. Okay, now, anyhow, I think you can do it. Now, the last question. Tough question. U is known, suppose, or whatever, because HLK, and then you can calculate whatever. Then Dr. Lee is asking in final exam, we like to find the optimum. You think about it. I will give you a few seconds. If you understand, tell me how. Because no heat transfer is given, no volume is given. But how we can find the optimum? I think this is very challenging. Is there any smart students?
Would you just use the peak and then
Okay,
find,
that's no problem.
then you would have Q and
I have a
V.
Q, I have a V, but still how?
Then I would solve the V squared over T times L cubed and solve Q also for V. And then you have
But
Q
no,
sub F is unknown.
no, problem is this I don't know. QF. You stuck. I said, yeah, you can get the maximum Q. You can get the maximum B, but still you cannot figure out the B and T. Anyone? The the power of the graph is more than equation. I told you equation is there somewhere in the book for optimum, but the equation is equation. The graph gives us some analysis like we are doing now. You just tell me how. I don't need the detail. Just one smart students.
Did
Just
you take the derivative of your q function and set it equal to 0 to solve first?
no. We did it already.
Okay.
You cannot do it. Anyone?
To use your AP value?
But still no way I can figure out volume. We don't know volume. We can know small v, but we don't know volume of the um 5 more seconds. Then we have to move on. I'm not gonna tell you, okay, because it's going to be in final exam. I'm not
Do we
gonna
have-
tell. Yeah.
Do we
what
have
is
the
it?
mass or the
No
test?
mess, no mess. No.
Oh.
1 second, 2 seconds, 3 seconds, 4 seconds.
Did you solve the little v for the big V and put that into the Q for
No.
APL?
You cannot. I don't think so. Time out. I'm moving on. Okay. Sorry. I teach everything, then you don't have to struggle. Sorry. Moving on. Radial fin. Radial fin. Okay. So radial fin, where is the radial fin? Yeah, something like that. This is another configuration. Inner pipe and the fin, radial fin. So radius R1 is a pipe, R2 is a tip of the fin. So what would be, and then thickness T. What would be optimum dimension? Obviously, optimum is R2 and thickness, because R1 is given, usually no optimum. So this is a question. Okay. Similar discussion. Then I think it's a little more complicated because we have to solve this is a little complicated efficiency. I think I'm sorry. I have to talk about efficiency. I skipped the efficiency. Now it's time to talk about efficiency. Where is efficiency? We discussed the efficiency, yes or no? I don't remember. I'm sorry.
You said something about beta, but think you
Not the
went-
efficient. Yes. Thank you.
but did you? Is there a new
Yeah, it's new. Yeah, it's new. Efficiency. This is important, very important. I think before efficiency, a little bit effectiveness. This is just the concept. Okay? So what is effectiveness? And then we talk about efficiency. You got to understand, okay? So listen carefully. This is totally concept, nothing to do with the math. So what is efficiency? Epsilon is actual heat transfer over the heat transfer at the base without fin. Okay, say there is a there is a plate. Okay, and we talk about this area. This is fin, actually fin. Okay, do you understand? This is T base. So the effectiveness is a QF fin over the heat transfer actual. This is actual over heat. It is kind of imaginary heat transfer over the base without the fin. So something without the fin. So what would be heat transfer without the fin is H. H is everywhere, and H is everywhere. And AC, this is area, base area, it must be AC cross section. And then theta B, theta B. So this is the small, okay, but sometimes in design of a fin, we like to know what is the effectiveness actual if we have a fin. But without the fin, so 5 times, 10 times, 100 times effect of a fin. This is a effect of a fin. Do you understand or not? I will repeat if you don't. Say yes.
Yes.
Yeah, one more.
Yes.
Okay, so effect of fin. If we have fin, how many times effective? That's the this. So higher the better. Fine. In order to justify, they say at least greater than 2. Less than 2 is don't use fin. No effective. Something like that. So we put the equation. Look at the equations. QF, we know that. I told you. Hyperbolic tangent MB and divided by HAC QB, and then a little bit arrange the same. So 2 parameter is coming. 2 parameter. One is K of H and P of AC. Well, this is a hyperbole. So in order to effective high, 2 parameter K of H is high, or something like that. So it should be high if we need a fin. So what is K is a property of fin. H. What is the H about air and water? Anyone? I think you should about. What is the air H about? It depends on the velocity, but no one.
Very small, like, is it smaller than one?
No, no. It's a 5 to 20 watt per. So water. Anyone? 5 to 20, something like that. About water, anyone knows? Come on. Huh? Guess. Tell me something. You are.
170.
Say something. I will correct.
Is it about 100?
1,000.
1,000?
Yes. 3,000, something like that. So big difference, age. Okay. This is order of 10. This is order of thousands. So what is a K of high copper? Anyone? Highest aluminum. Do you know? It's about 400. It's about 200, something like that, K. So K of H, if it is water, then this is going to be very small effectiveness. So do we need a fin or not? If it is water, probably. Do we need a fin or not?
For water, no?
No, because it's going to be very small number. It depends on this, but also, so probably we don't need a fin for water. How about the air? Air. K is 400 or 200, air is 5. This is going to be high. So we need fin or not?
Yes.
Yes. That's why now you look at the radiator of the car, gasoline engine. I think everybody knows, Americans should know what it radiator look like. The air side is a lot of fins. Do you see? Do you say yes?
Yes.
Yes.
Water side, there's almost no fin. Water side is pipe. Say yes.
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 Okay. That's what happened. Okay, that's what happened. The air require fin, water usually no. So now another question: P of AC. In order to make a high effectiveness, what would be shape of the fin with this? P is perimeter, AC is cross-sectional area. Now tell me, you're smart. What would be shape of the fin just using P and AC? A given volume, think about it. What would be shape?
It'd be skinny and
Yes.
long.
Yes, very thin, skinny, right? Very thin, skinny. Yes or no? So
Yes.
perimeter and the AC is small because of thickness, small, given perimeter. So this is going to be very thin. That's why we have a thin or thin. How to pronounce? Anyone American? Thin. Pronounce again.
Thin.
Thin. Yes, thin. Okay, thin. I like to learn from American students. Can you pronounce this?
Thermoelectric.
Thank you. One more students.
Thermoelectric.
Thermoelectric. So I say thermoelectric. Would that be looks good? Pronounce? Yes or no?
Yes.
I have a problem. I have everywhere go and thermoelectric. Nobody understand. Somebody says thermoelectric. Anyhow, yeah, that was my pronounce problem. Yeah, I know that. Anyhow, now what is next? Now we pretty much understand efficiency now. Okay, efficiency. So different, quite different. Don't confuse. Now efficiency, we use eta, fin efficiency. Okay, fin efficiency is actual over maximum. What would be maximum? The different story. So it's going to be less than 1 because it's a maximum. So what would be maximum? What would be maximum? What would be maximum? Okay. T infinity, H, T infinity, so anyone figure out the Q possible maximum using the symbol?
Or would 1 be the highest?
H is nothing we can do, and area is nothing we can do. Whatever given, so area. This is a heat transfer area. I think what is the area is A B whatever TL. I think this is area. No. This is volume. I think P perimeter times perimeter times B is about area. P. That might make sense. P times B. This is B, profile length. Anyhow, what would be a temperature maximum? Possible maximum. Because temperature is dropping here.
Is it T ambient?
No. Maximum
B?
temperature.
Or T base?
Temperature must be the difference. Maximum possible. I don't know. It must be a zeta B. I think zeta B, because this is zeta B. Zeta B. This temperature, right? T B minus zeta B is T B minus T infinity. So, look at that. This is the maximum. QF, H, PB, zeta B must be maximum. I think if you understand, say yes. Don't say yes if you don't understand. I will repeat.
Yes.
Yes.
One more.
Yes.
Okay. So 3 students. So, you know, the efficiency, very easily you can figure out Q max. Q max is easy. QF is HPB zeta B. Easy to remember. So once you figure out the efficiency, do you think you can calculate the actual? Yes or no?
Yes.
Yes. So what is you have equation H P A C, I forgot what was another. Huh? K zeta B hyperbolic tangent MB. You don't have to use these, okay? We look at the efficiency and then calculate the actual, because this is known usually. That's what I'm gonna explain. So it turns out if you look at it mathematically, this is it, easy. So in the rectangular is hyperbolic tangenta MB over MB, easy to remember. Once you calculate the efficiency, you can calculate the actual. That's the I suggest. Easy, much easy. Okay. Then you have to understand what is the efficiency. Higher the better? No, that's the problem. So if we plot dimensionless efficiency, this is some dimensionless, but it represents the HKAP is constant, is a B. Okay, BC is B plus T over 2, a little compensate adiabatic. But if we use a little length, then the B is actual. So a little bit add half of thickness, then usually it take care of the negligence of adiabatic tip. But that's why B is almost, I'm okay. This is so small. So it's the same, okay? Anyhow, so B, this is a represent the B, B. So efficiency is, if it is long, we understand the efficiency is low. But what happened if it is short, very short, is high. So don't think of efficiency something else, higher the better, no. What we need is very convenient. So you have to understand, otherwise you will confuse. So it turns out actually between 0.5, 0.7 is good in design. This is good design. If you understand, say yes.
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 One more.
Yes.
Yeah.
Okay. Okay. But you have to understand, otherwise it's confusing. That's what I'm telling you. We can use it. Good, fine. But don't think it's higher the better. No, that's not the truth anymore. That's it. So now we can use efficiency. Fine, fine. Okay.
Do we use efficiency with the,
Oh yeah, yeah, we use it. Yes.
no, I mean, to, if we only have the Q like you were talking about? This
No,
right here?
well, if you don't need it, don't use it. You know, QF, you can just calculate. It's okay. Don't use it. You can calculate QF if from the graph chart. What I put the name? What is it? Yeah, chart, general chart, whatever. General chart you can calculate, but you have to understand QF. QF is always you can calculate efficiency times H P B zeta B. Get it? And what is the efficiency? Is hyperbolic tangent MB over MB. It turns out 4 point, I told you, I forgot some number, 1.8 something. Big, you know. Okay?
Are you talking about beta or no?
Yeah. This is better. Yeah. This is better. Specific beta.
Okay.
Yeah. I'm sorry, this is not. I'm talking about beta. Yeah, I'm sorry. Beta is MB is 4.18 something. Okay. So efficiency is 4 point, I forgot the full name. Anyone remember what is of 1.8 something?
Uh, 1.419.
419. 419. 4. Jesus. Beta is 1.419. Totally. So what we can do, what we can do is efficiency of fin maximum. Maximum is 1.419, hyperbolic 1.419. I means 2. Okay, this is the maximum efficiency. That's what we found. Make sense now? Yes or no? We don't have to use these as long as we use this general chart. General chart maximum is that same 1.419. Make sense? Okay, this is so weird. Okay, now back. Radial fin. So everybody understand what is efficiency, but now is a radial fin. What is a radial fin efficiency is this. Don't ask me. We graduate school, we just solve analytically. And then what is Ki is a Bessel function. Do we have to know? No, we don't have to know Ki. Just a Bessel function. Okay. We use a chart. Okay, so phi is a ratio. R to C. Again, C is, don't bother with the C. Oh my. Sorry. It's something weird. Where is my? That's why I like to use book. I cannot use the book, this is copy of the book. I had a little problem. I have to use just one type of screen. I cannot use two, so that I cannot use my book. Once I book, I cannot use my PDF annotator. I like to use a PDF annotator. Please understand, I have a little difficulty my lecture. I lost the page where the,
It looks like it disappeared.
yeah, disappeared, so weird. I disappeared. Oh, Jesus. Oh, it's weird.
You push undo.
Say again?
Push undo.
Ah, thank you. Thank you very much. Now I can see. You saved my lecture. I don't know what happened. Okay, now I can see. So, but we understand the efficiency now for radial fin, everybody, right? No matter with the, Bessel function, it doesn't matter. But we have equation 268 And then we define the phi is a ratio. So the phi is a ratio R2 of R1. I told you R2 is almost the same as R2C. This is R2C is R2 plus T over 2. I told you the adiabatic tip things, it's okay. You can assume. Do you understand or not? Say yes.
Yes.
Okay, don't bother with the C, okay?
What's
It's-
the I and the K
What is the I?
in the efficiency?
Bessel function. You don't have to know.
Well,
Just
okay, so the C1, but what about the K1 and I1 and
it's all Bessel function, different
that's
type.
all of it? Okay.
Yeah, I0 and K1. Don't worry about that, okay? But anyhow, we have an expression. The Mescat can calculate Mescat, okay? So we don't have Mescat, so fine. I just used it. But anyhow, here we have a phi and psi R2 minus R1 H of KT. Once phi and psi, and I use that phi and psi, and I plot it. I plot it. Okay. This happened again. Oh. Yeah. Okay. Now, so we understand the efficiency and the psi, also phi here expression, and phi 1, 2, 3, 4, 5, 8. So once we calculate the psi, also once we calculate the ratio of phi, something we can calculate the efficiency. Okay, so those are the Bessel function. Make it simple. Okay, all you need is the dimensions. Okay, R1, R2. Then you can figure out efficiency. Okay, so move on. You can use this plot, but you need the dimensions to compute the efficiency. Once you have efficiency, it's easy now. Okay, because actual is efficiency times. Can you tell me now what is the maximum? Come on, what is the maximum? The heat transfer is, I don't know, let's say a total heat transfer area, AT. What would be maximum? You should know that.
Is that well, it's not the same as the rectangle, but is it?
Give me equation.
Q max.
Yeah. So what is that? H T infinity. The same business. Well, you can tell me a rectangular. Then say what is a rectangular? Give me rectangular.
H A sub C theta B. Or I mean, that's the effectiveness. I'm sorry. It's HPB theta B.
Okay, now radial. Can you figure out radial? HP is 80 total area. Give me. What is the Qmax?
Would it be the R2 squared?
No.
What is Q?
This is a rectangular. This is a radial. It's a matter of area only. Only matter of area. AP is a rectangular. The radial is a AT. So if area is AT total, this area is AT, then what would be maximum heat transfer?
Would it be HAT theta B?
Yes. That's simple. You know, all we have to figure out is AT. Then H is given, theta B, the efficiency. We will talk about it, but this is one of relationship, efficiency. Then you can calculate the actual, okay? So keep in mind, again, using efficiency, fin efficiency of that. Now, efficiency in terms of, look at that, phi and psi, look at that. Okay, now, optimum design. Optimum design. So again, look at that. Radial, we talk about radial fin. QF is efficiency times Qmax. So efficiency times Qmax. HAF, rather than AT, no, fin area, AF rather than, okay? AF and theta B, that, okay? Now,
Would AF? Oh, there's AF right there. Never mind.
yeah. What is the AF is a area, okay? Area. The okay, this is R1, and then this is R2, okay, and this is T. So what is the fin area is pi R1 2 square minus 1 square 2 pi, no, pi R square minus 2 pi R1 square. Okay, but the area is two area, this one and the other one here. So I had to multiply 2. Make sense? Yes or no? Yeah, yeah.
Did you say for R2C we can just use R2, or do we
Yeah,
use
yeah. R2C is same as R2C.
Okay, so we don't have to add the T over 2.
No. That's the small. It's bothering us. Okay, negligible. Okay, now, what is this? Do you think? 2 pi R2T is total area.
The side of the fin.
Yes, this one. Okay, so, but this is a small again. So I think is a 1% if you calculate. Maybe this is major. I think in final exam I don't bother with this, just this. You understand? So negligible tip area. In final exam, negligible, but practical. In after school, you design. You have to include it because you have enough time. Now, neglect it. If you understand, say yes.
Yes.
One more.
Yes.
Yes.
Okay. Okay. Make it simple. Make it simple. Don't use it. Yeah. Thank
Why do
you.
we multiply that term by 2 for the side of the fin?
Well, that is. Let me look at it. I think you have to say yes.
It's because 2 pi R is the
Oh, yeah. Okay.
circumference
Gotcha.
times thickness.
Yeah. So everybody, yes, right? Okay, now pretty much we figure out, because once you figure out AF, well then let's see. So now I think what time is it? 5:10. A little bit more. Am I right? More. I like to take a break. I have a headache. I'm sorry. I'm old man. I'll be back 10 minutes break. Okay? Yeah. Okay, I'm back, everybody. So basic structure of radial fins, I think we understand. And fin efficiency we discussed. And the fin efficiency, yeah, it turns out including the Bessel functions. That's why we have efficiency Bessel function. And then my work. I did a lot of my work. You cannot find anywhere in other books. So I developed. No, actually, this is not only my development. I did some work, but I learned from some other work. Anyhow, we defined U, similar U. So 2H now, not the L, R1. R1 is given, and then K, thermal conductivity of the material, and then power half. So U is mostly given, and then we defined lowercase w is R1 over T. Okay, R1 over T, and lowercase v is a volume pi R13 is a non-dimensional. Okay, U W V. So I try to express in terms of dimensionless. Q, I define QF over 2 pi K R1 zeta V. So usually denominator is known. Look at that, 2 pi K R1 zeta V is known. So actual heat transfer over some known value, I set capital Q. So the volume is now, is, you know that, pi R2 square minus pi R1 square times T. Okay, again, let me a little practice. Volume is a pi R2 square minus pi R1 square over T. Everybody understand? Say yes.
Yes, sir.
Yes.
Yes, say yes, if you understand.
Yes, I understand.
Another student? Or do I need to explain?
Yes.
Okay. You have to figure out the volume. Okay, now, so using U, W, V, Q, this QF, I try to express in terms of UVW, Q, UVW. Actually, I did it. UVW, everything, and then optimized. This is a tremendous work. What is dW, dQ, dW, differentiate, let it to 0. This is the result. Okay, choose the work. And then I found this. This is has to satisfy. So I very complicate the optimized. Then kappa 1, kappa 2 is expression. Another kappa 3, kappa 4, and C1, whatever. And solved. This is the solution. This is the solution. Okay, this is U. So it turns out now this is Q. Hopefully you understand, similar to the rectangular. U is this, and dimension R1, R2, T. That's it. And then U value, and then this is optima. Everything is optima, turns out. Not like a rectangular. This is a little weird. Not everything is optima. Okay, for example, 0.6, this is all optima. All optima, if it is. So once we have a QF, for example, QF is 0.3, 0.1, 0.2. Because sometimes QF is given, then I can figure out. Then look at that. I can figure out W. W is 2, 3, 4, 5, 6. W is 6. Once W is 6, I can figure out the T. Do you see that? So once I have T, T is R1 over W. So whatever, I can calculate the T. Then there's another curve. There's another curve. I said that we know the W. Then I said the 0.6, if it is 0.6, is everything is optimum, but now is a W. What was it? What was a W? Anyone remember? I forgot. Well, whatever we have to calculate. I don't know.
R1 over T.
Yes. I have to calculate. And then I have to figure out V. Once I have V, then it will tell you volume. Say yes. Once I have a V, I can get the volume. Once I have a volume is, can you figure out the volume is pi r2 square pi r1 square over T. So T is known, volume is known. Do you think you can calculate the R2? Say yes.
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 So is
Then,
T, since
then
is T known now, if it's not so that's not one of the or that is one of the optimum.
say again.
So T, you're saying T is known. Is that
No,
because we know
not
W?
known. Not known. We calculated the T first, and then I calculated the T2.
Right, because you calculate it with W or
Yes. From W, I calculated the T, and then from here, second chart 2, I calculated the R2. Finish. Something similar. Okay. So I optimized. And then I can calculate now. Another question. Once I have R2, T2, do you think you can calculate efficiency? Yes or no?
yeah.
How? Just tell me how.
Well, you would find QF and divide it by Q max.
No. Anyone? How to calculate the efficiency?
Oh, from the first chart?
I said that we optimized R2 or T, then how we can calculate the fin efficiency? Are you gonna go Bessel function? No, we don't have a Mescat, no way. How we can figure out the,
Is it figure 2.7?
is that the, I don't remember 57, something like
Yes.
that.
Efficiency on one side and R2 minus
Cause-
R1.
Kasai and
Kasai on-
yes, okay. Thank you. You're right. Phi is a R. I think is a T. Yes or no? Maybe yes. And Kasai.
Oh, it's R2 over R1. Phi?
No, yeah. Phi.
Isn't it R2 over R1?
I'm sorry. Yeah. Thank you. My memory. And then Kasai, I think Kasai, I forgot.
It's right below the figure on the screen right now.
Oh, yeah. Thank you. Kasai is that. So if you know this, you can calculate Kasai, and then Phi and Kasai, you can figure out the efficiency. So once you have efficiency, how do you calculate the actual heat transfer to the fin? Anyone? How?
It's the efficiency times H area of the fin theta B.
A of fin times theta B. So all you need is A of fin. Then you have everything. You can calculate this, you can calculate this. Very, otherwise it's very complicated. You have to really, from the chart, you get it, and then from the chart, you get it, and then immediately you can calculate efficiency. Otherwise, it's very complicated, I told you. Maybe sometimes a book example is not the good way. I forgot it. I was confused maybe, but this is a good way. Okay, now back to maybe several question. Again, the same concept. Maybe QF is given. Do you think you can calculate optimum? Yes or no?
Yes.
One more.
Yes.
Okay, now second question. If the volume is given, do you think you can optimize? If volume is given, now, if volume is given, yes or no? Okay, I think yes. If volume is given, you can immediately calculate R2. No. I don't know. T and R2 is not known, but how we can figure out?
You would find little v.
I think you have to a little bit struggle using these two charts. Volume is given,
So
then
could
you
find little v
know the
and
V. You know the V. Once you know the V, I think you can calculate the W. Once you have W, you can calculate the T. Yes, you can do it. Something like that. Well, again, I think without any constraint, I think you can do it, but that is too difficult. Yes, also you can do it. Yeah, but that is too much. But anyhow, at least I think we are done now. Now, I'd like to move on. What time is it? What time is it? 5:30. Yeah, we have time. I'd like to move on the multiple fin. We call heat sink. Okay, I think we are ready to heat sink now. Something. Do you think you have a lecture 3? Yes or no? I don't know. Do you have lecture 3?
A handout?
Oh, I don't have to. I'm saying you have a book. I'm sorry. I don't have to show you. Yeah. So I have a lecture 3 is everybody has book now? Yeah, I'm sorry, it's a little expensive, but you should have it. Otherwise, problem. Yeah, this is, look at that, something like that. 60, 68, 69, yes. Something like that. Multiple films. I think we have ideas of a single film, but now we have a multiple film a little bit, extend and optimize it, okay? So not difficult. But the problem here is if it is a natural convection, so it's getting warmed and then the boundary layer here, boundary layer. So it's a complicated moving upward air. If it is natural convection, if forced convection, yes, forced convection, 2 case. So I think we have to go back. Do we have chapter 1? I think chapter 1 and heat transfer. If you go back, chapter 1, there is some talk about the natural convection and the 2 vertical plate, not only 1. Free convection. Yes. So free convection, which means is quiescent air, but the plate is warm, the air is cold, or maybe opposite, but so the near the plate, it's getting warm and it rises because the warm air density is lighter than cold density, so it's rising. That's the free convection. So this is one plate is rising, and then here is a quiescent. That's the velocity is 0 here. And then velocity is moving, something like that. Temperature. So we discussed the Rayleigh number for convection. Z, I think I have to, yeah. Rayleigh number is important. Gravity. This beta is not the optimum beta. This is expansion coefficient. Keep in mind, expansion coefficient is temperature, film average temperature inverse. So either you can, for ideal gas, you can use it. So you don't have to look up a property appendix for beta. You can just calculate inverse. Otherwise, temperature of surface, ambient, L, and kinematic viscosity, and the thermal diffusivity. So in natural convection, we suggest for air, okay, in air. So 0.157 Rayleigh number. Once I have a Nusselt number correlation, then you can calculate convection coefficient H using L and K. But always the Nusselt number K is fluid, always. So not the solid K, fluid K. You have to be careful. So Nusselt number using K, you can calculate the convection coefficient using Rayleigh number. Say yes. Hopefully. Say yes.
Yes.
Yeah. I think a very typical analysis. This is the vertical plate, but if we have two plate, we suggest Lm bars. Lm bars. Don't ask me why. We just use it. Lm bars is different. A little careful. Rayleigh is not normal. L, we use Z, power to the 3. Otherwise, it's similar. So a little bit, that's why G is spacing between the plate. Two plate and spacing, this is Z. So Lm bars defined, something like that. And then Nusselt is Lm bars. This is the equation. I think you can use equation and then you can get the average. And then compare to the experiment. Beautiful. Because Lm bar is a dimension, something like spacing. So this spacing is from small. This is one physics, small. If it is too large, another physics. So two phenomena converges the meaning. You don't have to worry about it, but something like that. So Nusselt number is two phenomena is converges. Turns out this is good optimum. Turns out. So Ln bars is look at that. This is the equation. You can use it. A little careful. G instead of L. Okay. In order to use Ln bar, you have to follow this this. Okay, let's go back. What was that? Yeah, okay. So probably we can figure out if there's only one vertical plate, don't use a bar. Okay, just one vertical, as I told you, 0.517, something like that, simple one. But once we have two plate, then optimum problem, the spacing. So we have here now optimum is not only a B is a profile, B is a profile, and the T, anyone? We need one more. What would be one more for heat sink?
Z.
Yes, spacing. So you have to look for these two, probably very close to the single fin. But the Z is you have to use Allen bars. Allen bars. Okay? As I mentioned, you can look up the Allen bars. No. I'm sorry. This is H. Even H is Allen bars. Allen bars, H. So G is still, we need a little analysis. I'm sorry. So we look up Z. I don't want to go detail, but we do have analysis for G, small and large. Okay, small and large, two case, I told you. And the small case, we figure out is proportional square of Z. For large, you know, for 157, I figure out G is inverse. So that it's very interesting. Two phenomena are large. This is large. This is small. I told you there are two phenomena. Okay. So I think we figure out equations equate heat transfer, small and large. Analytically, we found the 2.3 Rayleigh inverse quarter, but later, Barkon and Rosano. Barkon is a Minnesota professor, Rosano, MIT professor, they found it. And then experimentally. So you have to use this. For free convection, heat sink, you have to use this. Optimum 2.714 Rayleigh, you calculate. L you have to include. Say yes.
Which one do we use then? The 2.3 or the 2.714?
This is experimentally proved. This is analytically. Which one are you going to use it?
So we're going to use experimental?
Yes.
Okay.
But this experiment is based on the analysis. So without the analysis, very difficult to get it. That's why theory, analysis is important. Power, inverse, Rayleigh number, quarter. That is what we found it analytically. Then we just coefficient a little bit improved. Okay. Rosano is a legend in MIT, mechanical engineers. Okay, well, we just use it, the result. This is free convection. And now forced convection, not free, like that, the forced convection. I'm not going to go detail, but similar discussion, look at that, narrow channel, large channel. And we found this. This is a forced convection. We need a Rayleigh number, Prandtl number, and the optimum. Say yes. So you can optimize spacing for forced convection and free convection. Say yes.
Yeah.
Yeah, nothing is very simple. Once you understand, simple. Okay. The detailed derivation, you don't have to worry about. This is too much. Okay. Some graduate school we do that. We just use the result. So two space optimization for free convection and forced convection. Okay, now it turns out some analysis, I hate to show these, students are confusing, but it turns out for free convection only, not the forced, it turns out the optimum spacing is the same as the thickness optimum. But extremely careful students don't understand and just use it. It's a problem. I really hate to show, but I think you have to calculate individually. Okay, you can do it individually rather than using these. It look like simple, but students make mistake. Okay, does that make sense or any question? Now, analysis. I think everything you understand. Look at that. The multiple fin, single fin, first of all. Single fin, rectangular. So F is a single fin, which means, okay, multiple I use a total or T I use. So single is F, we distinguish. So single is a single fin efficiency, H, single fin area, zeta B. We know that. Now a little bit thermal resistance is defined temperature difference over heat transfer. That is a resistance. You have to know that. Everywhere in thermal design, they use a thermal resistance. Once you have equation, everything, the thermal resistance, immediately you can calculate temperature difference over heat transfer for single fin. Okay, now multiple fin is Q total now, not the single, or QT. sometimes they use QT, is efficiency overall, not one, overall times same Qmax HAT total and zeta B totally. So this is using the efficiency, very easy concept, even heat sink. I'm going to repeat. Now, overall resistance, maybe overall, is zeta B Q total. You can calculate. And Q total is overall efficiency. We will talk about it later. But anyhow, overall efficiency, not only one, heat sink, multiple, times Q max. So overall, it's the concept is maximum possible H, AT, zeta B, all. So once you have a single fin efficiency and the single fin area, I'm telling you, just overall is 1 minus A single A T 1 minus single fin. I think so. I think somewhere. Yeah, look at that. Yeah, I think the detail, you can look at it, but finally, overall is 1 minus N. I'm sorry. So, N. N is a number of, N is a number of fin. So total W is a total width divide what would be number of fin is T plus what is the thickness between the fin is Z. Do you understand this? Number of N, not the eta, N. Number of fin is W divided by T plus G. Do you understand?
Yes.
Look at that. W is a width. Divide G and T. T and G. That is give you N. Okay. So I think total overall is this. Actually, a little bit. So total overall is zeta B of Q total. So Q total is overall and Q max H A T zeta B. So that this overall H A T is Q T O zeta B. So R TO is theta B of QT. It is overall HAT. That's interesting. Overall thermal resistance is eta HAT. So a little bit here, total resistance is, you have to remember, overall HAT. AT is a total heat transfer. This is very useful. No matter how complicated, turns out this is it. So now, do you think you can handle how to optimize it? Is I accept. It's not exactly same. Single fin, I accept. Single fin optimize so that B and T, and then G optimum, then this is heat sink. I accept. Not exact, but I will accept it. So you can design heat sink. Yes or no?
Yeah.
Yeah. I think you can do it. You can design heat sink. And then you can calculate the overall. Yes. You can calculate the total. Yes. That's everything. You solved it. But probably you need to look at radial fin optimization. Yes or no? Single fin, radial fin optimization. Yes. Okay. Homework. 2.8, 2.9, 2.11, challenging. 3 problem. I think you have to go through some example problem and do homework problem. Okay, using general chart. Chart 1, chart 2 for radial fin. And also you have to go to general chart for rectangular fin. Everything. Using efficiency. I told you. Then it's a very simple. Efficiency. Keep in mind, efficiency. Then it will give you heat transfer. It will give you total. All you need is AT, AF, a little bit, NF, efficiency of single fin, and then overall, then you can solve it. No difficult, heat sink.
Professor, I don't know if they've talked to you about the remote desktop is not working right now because of some IT issues for the past few days. Do you know when that's supposed to be fixed?
Yeah. I'm gonna talk about it. Yes, thank you. Give me 1 second. Oh, do you think you can optimize it? Yes or no?
Yes.
Yes. You can do it. You can figure out the single fin and multiple fin, G. About Mescat, we are working on that, license update. So it takes time. I don't know. We still, deans, chairs, and myself working on that. So anything homework related to Mescat is removed right now. Don't do it.
I mean, the remote desktop isn't even working. So I'm in your DOTS class, design of thermal systems. Are we having lab this week? Because there's no remote desktop.
I don't understand. What is a desktop? Computer?
How we sign in from computers from off campus to sign into computers on campus? To use ANSYS and stuff from home?
Yeah, I will check that. I'm sorry.
The Global Connect is working, but it's not recognizing computers to be part of the network.
Okay, let me check. Okay.
Okay.
Yeah, let me check the CAES computers.
Yeah. We
yeah,
can't we can't log into any computers right now because of the IT issue that's going on.
Okay, I will check that. Okay.
All right, thank you.
Okay. Any question? I'm done today. It's a lot of work, but I hope you enjoy and you have now power to optimize heatsink.
When are these problems due?
Next class.
Okay, thank you.
Okay, I will announce it through the Dropbox. Okay, thank you. Bye.